Hi, I'm Vincent.
And I'm Leah. Welcome to Math Happier. Today we're talking about conditional probability.
What is the condition of the probability? Good condition? Poor condition? Do terms and conditions apply?
Well, actually, you're getting kind of close with the last one.
So conditions do apply.
Yeah, once we know something has happened, we can condition on that probability.
Oh, I see. So if we want to calculate a probability based on a condition that affects the probability, I bet this applies to cards.
Yeah, it does. So imagine you've got a brand new, well shuffled deck of cards. What is the probability of drawing an ace?
Well, there are four aces in a deck of 52 cards, so 4 in 52,
Mhm.
or 1 in 13, or about 7.692038%. Oh, lucky me.
Great. So now keep your card, draw again. What's the probability now of drawing an ace?
So already having an ace is a condition that affects the probability of the next draw.
Absolutely.
Okay, so there's three aces left, so I'm going to guess 3 in 52.
I agree there are three aces, but we've used up one of the cards in the deck.
Oh, right, Yar. So 3 in 51.
3 and 51.
Not this time.
Mm.
We should look at the notation for conditional probability. If we have an event A that has already occurred and we want to know the probability of event B then occurring, we say the probability of B given A.
We write that P parenthesis for probability of, followed by the event that we're still curious about, B, then the vertical line for given, and the event that we've conditioned on having happened, A. Close it off with one more parenthesis.
Can we do some more examples that involve counting cards based on the cards you've already seen?
Vincent, how many times do I have to tell you we are to use our power of statistics for good, not counting cards in Vegas?
I mean, doing math now is apparently the same as cheating. So, okay, what did you have in mind?
Public health and safety. The standard HIV test is very quick and accurate. However, no test is perfect. While there is very little to no chance of a false negative, there is some chance of a false positive. In the results of 10,000 HIV tests, we got the following. There were 9,780 negative test results, of which none of them were a false negative. Of the 220 remaining tests, 20 of them were false positives. Now, my question to you, Vincent, what's the probability that a person actually has HIV if we know they tested positive?
Are you serious?
Yeah, man, you've got everything you need to answer this.
Okay, I'm gonna need to organize all that information you just blasted at me. So I'm gonna use a two-way table because we have two variables. Our first variable is whether or not they test positive, so I'm gonna put that in the rows. The other variable is whether or not they actually have HIV, so I'll put that in the columns, and then I'm gonna add total rows and columns because that's always helpful. And then that leaves this blank spot in the middle, um, which is the people who've tested positive and actually have HIV. And I can figure that out because the row totals have to add up. So by subtraction, I can tell that is 200.
Precisely. We're ready to put it all together. We know that they have tested positive, so we can condition on that top row of testing positive. This total will serve as our denominator, total people who tested positive. Then the numerator will be the people who both tested positive and actually have HIV.
Okay, so 200 out of 220, or about 91%. So what you're saying is there's a 91% chance that someone actually has HIV if they have tested positive for it.
Absolutely.
And so the general formula, can we put
Mm.
this together into some sort of...
Yeah, we can apply this to the general situation of probability of B given A equals probability of A and B over probability of A.
Maybe we should do a simple example with that formula. Let's say, I don't know, I'm a math teacher, and 20% of my students get A's, and 65% of them turn in all the homework. And I want to know what's the probability that someone gets an A if they turn in all the homework. But here's the thing. those are not independent, right? Because obviously turning in the homework raises your grade.
Mhm. Okay. So the condition is doing all the homework. That will serve as our denominator, probability of A. But we still need the numerator. What's the probability that a student does both, gets an A, and turns in all the homework?
Oh, okay. So that I just checked my records is 17%.
17%. Great. So 17% get both an A and did all the homework. 65% did the homework part, so making that into a proportion. Oh, okay, so 26.2%.
Okay, so overall, 20% of students got A's, but of those who did all the homework, it was 26.2%, which you know what I just realized? It's a higher probability of getting an A if you do all the homework.
Wow, who'd have guessed?
Hey, let's do this example. What's the probability that she's going to text me back today, given that it's been 3 days since she's texted me?
Oh, sweetheart.
So as a probability, what are you saying?
Have you ever heard of scientific notation?
We need a bigger sample size.